Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So in the last lecture we were talking about the properties of localized surface plasmons. We looked at what a localized surface plasmon resonance means and how does the size of the nanoparticle affect the resonance. Well, I showed this slide already to you. So when we were talking about how to excite these surface plasmons, we said that if you look at the bright field image, the bottom one is the bright field image, you see that there are these specks which are there, which represent the nanoparticles. But you see that the speck is very, very small. These tiny specks you see, these are the nanoparticles. If you look at the extinction cross-section of these nanoparticles, it's reasonably larger than the geometric cross-section, geometric size of the nanoparticle, but still it looks like a very weak effect. So we'll have to resort to things like dark field microscopy to actually look at how these nanoparticles respond. Okay. And we've also seen how the geometry can affect the resonance position. So we have explained only the nanosphere, but even other geometries can exhibit this, and depending on the geometry, the resonance position changes, as you're seeing here. Now for applications, we would like to actually tune the resonance. Okay. We don't want it to be dependent on, we want the resonance to be easily tunable. So what are the factors that make the resonance tunable? For one, we already understand that the resonant wavelength depends on the optical constants of the medium, or rather the nanoparticles, and also of course the medium, right? So what happens if you have, let's say, it turns out that, let's say if you have silver as a metal, now if I have silver, my LSPR is going to be towards the blue end of the spectrum, or slightly blue shifted, okay? Because the silver has a low loss, and you'll have to look at where the real part of the dielectric constant goes to -2, and then we see that is the position where you get the LSPR resonance for silver. Similarly, if you have gold, you will see that it's slightly reddish, slightly red shifted compared to silver. All right, red shifted means it's going to longer wavelengths. But and also if you have a surrounding medium, let's say water, the resonance is going to be different from when it is with air. Why is that? Well, if you remember the polarizability, you will see that the denominator has epsilon metal plus 2 times epsilon dielectric, right? That surrounding medium. So if the surrounding medium dielectric changes, let's say from air to water, so I won't write the entire expression, but essentially the factor was something like this. The denominator was epsilon metal plus 2 times epsilon dielectric, right? So if I change my dielectric position and say this is, okay, the numerator was epsilon metal minus epsilon dielectric, right? And then there are other constants. So if I change my dielectric, this guy, from let's say from air to water. Water has a refractive index of 1.33, so you can actually compute what is its dielectric constant. Well, we also have to look at the dielectric constant in the visible frequencies, okay? So if you do that, because this is now red shifted, the resonance will again be red shifted here. The resonance position, as you go to higher, if the surrounding medium's dielectric constant increases, then the resonance will be red shifted. Okay, we'll give you a small problem on this in the homework. Please try it out. We'll give you the dielectric constant for, let's say, silver or something, and then we will ask you to compute what happens when the medium is air, what happens when the medium is water, and so on, or ethanol or whatever. We can compute these things. But still, it doesn't give us a lot of control. So people have looked at it for a long time, and what they have found is, if you have, let's say, a nanorod, we just discussed the sphere, but even if you elongate, you have the plasmonic resonance that occurs, and now the quasi-static approximation breaks down, and as you increase the size, the resonance gets redshifted, right? We talked about that. So you see that exact thing, you make the nanorods now of different aspect ratios. Aspect ratio means this is the length of it and this is my width. if I make it longer and longer for a constant width, I'm increasing the aspect ratio. If I increase my aspect ratio, you see that immediately the color of the solution, this is a solution containing the nanoparticles, and that is actually red-shifted. So the size, increasing the aspect ratio, is shifting it to the red. Similarly, if I create a core shell nanoparticle, so we are essentially trying to gain more degrees of freedom. If you have a simple metal, gold nanoparticle, we can only control to some extent. Now, if you increase the size as well, it's better. Now, in addition to just considering a simple sphere, I'll consider a sphere surrounded by another shell, let's say a cricket ball, right? Inside there is some core which is consisting of various materials, and then the shell, which is a reddish thing, right? Leather, which protects the insides, right? So the core shell kind of structures that will again give you a lot of flexibility. So in this case, if you have a core shell structure, inside there is metal and then there is a surrounding dielectric. Let's say I can increase the thickness of my shell, and as I increase, I see again the resonance position is shifting because the color is changing. Similarly, there are a whole variety of materials that are done, investigated. And, for example, they have considered what are known as nano cages. Essentially, you have some amount of gold encapsulated within a cage-like structure. And it was shown that as you increase the gold percentage, again, the resonance is shifting. All right. So the whole idea is that how do we change my resonance positions? Because that has a lot of applications in the field. All right. So, but even in spite of all of this, you see that we are talking about resonance in, let's say, liquid. That's not very convenient because, if you have to change the entire liquid, it becomes difficult, right? It's okay for when you're considering in the body, but in vivo, but even then, sometimes you want to have structures without surrounding dielectric, let's say in air. How do we do that? There are, of course, fabrication processes that can help you do that. So here, I'm just showing you some examples of how you can tune a LSPR resonance, okay? Now, we have already just mentioned that if you have a nanorod, it will exhibit a resonance. Okay, how does the resonance look like? In the case of sphere, we saw the dipole mode, isn't it? Wherein you saw that the electric field is located on both edges. So we said that is positive and negative. That we said is actually we know the charges from the simulations. So the exact same thing is being done here. Let's say you have a nanorod which is exhibiting hotspots. Hotspots means compared to the background, how much more stronger electric field is present at that particular location. And immediately you see that there is a lot of electric field that is concentrated. This is a color picture, and the scale is going up to 4,000 in terms of relative intensity, E square. So you see that on the edges you have this hotspot, and that's a sharp electric field that is exhibiting. So that's a resonance. And if you look at the current density in that, you can actually plot it in a simulator. You'll see that the peak current density is occurring in the center. Okay, just like a dipole antenna. All right. And if you look at the charge distribution, you'll see that it is having, let's say, positive charge on one end and negative charge on the other end. Okay. This is simply having one single antenna. Okay. But now if I bring two such antennas, I make a dimer out of it, as I'm showing in the middle picture. I have two antennas which are brought together. Now, there are resonances in both of these structures, and the resonances will interact, right? And what happens is you get, let's say, compare the electric field here, compared to the single nanorod. If you have two of these nanorods, you are able to see that if I decrease my gap, I'm seeing a significantly larger amount of electric field. Okay. And now what happens is the current density is distributed. There are two peaks in each of these antennas. And then there is this nice charge distribution as well. So there is a positive and a negative in the center, and then there's a positive and negative on the edge. The overall charge in the nanorod has to be conserved, right? But because of the existence of this, interaction of these two, it looks like there is a very strong dipole that gets generated. And now when I say that this is a dipole, immediately if I change my distance, I'm going to be able to tune the dipole position. And that is what is shown here. If you bring the rods closer, you will see that the electric field intensity has become much more stronger. So you have a very, very strong confinement of electric field. And then of course the charge density as well shows a similar trend. So nanorods are not the only geometries. You can, this was some antennas that I fabricated long back. So essentially you have ellipses. You can think of these small discs, and if you reduce the distance between them, again there's a dimer and there's a strong electric field. And people have investigated a whole lot of structures. Another example is basically having two of these rods and then one rod perpendicular. So this exhibits an interesting property known as electromagnetically induced transparency. So a lot of research has been done. But why do we want to increase a hotspot? Well, the whole premise was that diffraction limit tells us that we cannot confine light below, let's say, lambda by 2. But now immediately you see here that this size, this scale bar here is 20 nanometers. So this is roughly, on the order of 20 or even slightly lesser than 20 nanometers. You will see that there is a very strong confinement of electric field. So we are able to go much below the diffraction limit. That is why it is interesting. Okay. And once you are able to enhance the electric field, you can do a lot of interesting things. For example, you can actually use it for sensing. Okay. I'll just talk about it in a few minutes. All right. So this is how you can tune. I mean, this is by no means exhaustive. If you open the literature, you'll find like thousands of papers talking about resonances and tuning them and so on. The essential idea is what I've told you. Every one of those LSPR resonances has to follow these ideas. All right. But the geometry can become more complicated depending on the amount of equipment you have and the manpower you have. You can actually do a lot of things. All right. So that is about the dimer. Okay. But how do I understand? This is, by simulating I can do that, but I also want to get an intuitive picture of how the resonances are changing. Okay. And in that process, there's a concept known as plasmon hybridization. That's a very intuitive concept that helps us understand how these resonances behave. Okay. This is published by the group of Peter Nordlander. And by the way, I'm sorry, this is actually 2003, not 2013. All right. So what he proposed this way back in, almost 20 years back, and they are essentially borrowing ideas from the atomic orbital theory. Okay. Let's say you have a LSPR resonance in a sphere. Okay. So I have this sphere and it has this characteristic resonance, which is, I'll represent it by energy level now. Okay. So each resonance I'll represent it by energy level. So for a sphere, I have one energy level, and let's say this is a dipole resonance. So you have this charge plus and minus separated out. Now I'll create another structure, which is basically a cavity structure. So instead of making a sphere, I'll take an entire volume of, let's say, gold and etch out the center. So I'll make a hole in that. If I make it, again, that again exhibits by what is known as Babinet's principle. It also exhibits plasmonic resonances. And the resonances are again going to be determined by the size of the size of the hole and so on. Okay. So now what I'll do is, I'll design my size of the hole in such a way that the resonance is slightly higher energy. Okay. I'll make it smaller. If I make it smaller, it becomes blue shifted. That means it goes to higher energy. If I make it larger, it gets red shifted and it goes to lower energy. All right. So I'll design in such a way that I have these two resonances. Okay. Now, if I combine them, what happens? Okay. Well, you intuitively if you have studied some amount of chemistry, you understand that there is this hybridization that happens. Essentially, hybridization means that you have these orbitals which represent the way the electron clouds are distributed in space. And then once you bring them closer, what happens? sp hybridization, S and P, right? Hybridize to form sp hybridization, sp2, sp3, sp hybridization states. Similarly, you take these two resonances and I cause them to interact. How do I do that? Well, I can make a ring structure. Essentially, I have the outer shell, and if I combine this, essentially if I make this, I remove the center part of the sphere, then I have a ring structure. Then what kind of resonances will it exhibit? That's a question. Okay. Now, in this case, what happens is, because they're very close to each other, there's a strong interaction. Now, the energy level of the sphere and the cavity interact and form two resonances. It leads to essentially each of these individual structures contribute one resonance or one energy level, and the energy level split into now two of them. And the amount of splitting is going to be determined by how much interaction is there. All right. So what happens in this case is, you have two resonances now, two resonant modes. What do I mean by two resonant modes? Well, in the previous cases, what you saw was, if I take the spectrum, let's say reflection, transmission, whatever, absorption, you will see that there was this peak that represents the excitation of a plasmonic resonance. Now what happens is, you'll have two peaks. Okay. For example, you'll have one peak at the lower energy, which is like this, something like this. All right. And there's going to be another peak, which is at a higher energy, which is something like this. I'll tell you why the peak is narrower. Okay. The reason is, so basically you have these two modes that are getting excited, and the bottom one, I can call it as a bonding mode, let me call it. Okay. Bonding mode or symmetric mode, bonding or symmetric mode. Okay. And the top one, I'll call it as anti-symmetric or anti-bonding, whatever. Okay. Just like what happens in your case of in chemistry, right? How the orbitals interact. So Now, why am I calling it symmetric mode? Well, if you look at the charge distribution, I can have various combinations. In the presence of an electric field, I can have positive charges on one side of the ring and negative charges on the other side of the ring. So there is a net dipole moment. Okay, in this case, there is a net dipole moment which is strong. If you have a structure has a net dipole moment essentially means the charges have separated. That's okay. So if you have a net dipole moment, it radiates. Why? Because when your structure supports such a dipole moment at that particular energy, if you come in, you can create this separation of charges, and that's why it interacts very strongly and it leads to resonance, right? So that's why you have extinction. Let's say it shows a peak like this, and the peak is going to be broad because it can couple in, the light can couple into the nanoparticle and couple out as well. So the radiative losses are going to be high. That's why the width is going to be strong, large. Okay. Larger width because of radiative losses. All right. Similarly, I can have another charge configuration which is shown on the top here. Now, instead of both positive and negative on one side, I can have a combination of positive negative like this and positive negative like this. And now what will be the net dipole moment in this case? Well, now you can think of in principle two dipoles. One is this dipole and one is this dipole. The net dipole moment reduces. And because of that, it does not couple very efficiently. Okay, does not couple efficiently to free space. So if I come in from a large distance, far field, what is known as far field, you will not be able to easily excite. And of course, because of that, even whatever energy is stored, it's going to be stored in there. It's not easily going to come out. That's why the line width is the anti-bonding mode will have smaller line width. That means lesser amount of radiative losses. Okay. So this concept is a very interesting one because it's not only relevant to this structure, but I can even think of structures like the dimer that I considered previously, right? So wherein you had, let's say, one dimer and the second dimer. The distance between them is what I call as D. So if I come in with that sort of a structure, what will happen? Again, I showed that the resonance was redshifting. I'll explain to you briefly why it's redshifting. The reason is, if you look at this famous picture in solid state physics, right? Whenever you study electronics, they'll draw this S and P, and then the energy levels are there, right? Let's say in this case we are considering identical nanorods. Okay, so if my distance, if this is my function of D, when my distance is large, I have energy level. Each nanorod has the same energy level, okay, because the size is same. But now, if I try to reduce the distance, if I bring the nanorods closer, I'll see that there is this hybridization that happens when they interact strongly, or when you are in the near field, they'll interact and they end up giving you one resonance which comes down like this, another resonance which sort of goes up. So effectively, this is my, let's say, bonding or symmetric, and this is my antisymmetric. And this is my, in terms of frequency, is what I'm plotting. Okay, that's what energy, right? Energy, H cross omega is frequency. So H cross omega is energy, omega is frequency. So now, because of the interaction, you have this asymmetric and symmetric bonds forming, or resonances forming. And the energy of the symmetric mode reduces as the interaction reduces. As the distance reduces, right? So that means that the resonance is going to smaller energy or smaller frequency or higher wavelength. And the anti-bonding resonance does not easily couple, so usually you don't see this. And we will see that only the red shifting of the resonance happens. This is what usually most of the times you see, because you can couple to it easily. This is going to be very, very weak from far field. Okay, that's why you see that the resonance is getting redshifted. This is another way of looking at the redshift of the resonance. All right. Okay, so good. So what? I have these resonances and I understand them pretty well now. Okay, what are they useful for? Well, there are a lot of things that people are looking at. Okay, one example is basically what is known as photovoltaics, wherein I want to look at what happens. I'm converting, let's say, solar energy to electricity, right? I'm interested in improving the efficiency of the solar cells. The point is that if you just expose a simple solar cell, it's going to convert some amount of light into energy. The efficiency is there. But if I can now somehow concentrate light in the solar cell, how can I do that? Well, let's say I have a resonance structure which actually focuses and light into that small scale. Then I can use the light to actually improve the efficiency of the solar cell. Okay. So this is one of the direction people are looking at, how to use plasmonic resonances to improve the efficiency. People have, now a lot of work has been done. That is one example. Okay. Another example is, let's say you have already seen the colors that these nanoparticles exhibit. Now I can actually design a periodic arrangement of nanoparticles so that I enhance the response, and I can create a structure something like this. I have a pixel consisting of different arrays with different size, dimensions and so on. So immediately if I shine light on that structure, I'll see that each particular subarray is going to have a different color. So I can actually create some sort of a filter. That liquid was not very efficient, but the moment I have, let's say, a periodic arrangement of, let's say, subwavelength arrangement, then I can actually control the colors of the structure. Okay, this is also called a structural color and stuff like that. This is very, very robust against degradation. Okay, so you can actually make a lot of color filters which are out of these nanoparticles. Why? Well, let's say I want to create, let's say I have my CCD camera, right? I'm looking at RGB in that. Now, can I somehow make it smaller? In the traditional CCDs, there's a limitation of the size because of the way the electronics works and all that. But now with this, you can try to make it even smaller. Okay, there are some efforts in this direction. Okay, another example that's very interesting is in what is known as molecular diagnostics. So we have all this PCR, ELISA, and so on. I don't really know the details of those things, but essentially techniques that will help you detect the presence of a particular antibody, right? So essentially, let's say the RT-PCR is basically, PCR is polymerase chain reaction, RT is reverse transcriptase or something like that. So essentially the PCR, right? So essentially you have a small virus, let's say the COVID virus, and then you want to multiply it many times. You perform this PCR and then you find out what it is. So essentially these are very sensitive techniques, but it takes time because you have to have so many cycles. For RT-PCR, I think the threshold was about 24 or 30 cycles or something. So if you want to improve the efficiency of these things, these PCR reactions and things like that, how do we do that? Well, the idea is that you put a nanoparticle, you attach these antibodies to the nanoparticle, and now that can help enhancing the reaction rate. Okay, that's why you can actually improve the efficiency. That's one way people are looking at. I'm no expert in biology. I hardly understand anything. So, but you can go and look at some of these reviews that I mentioned here. And if you're interested, you'll find a lot of work wherein, looking at nanoparticles, looking at simple gold structure, I'll create some sort of attach some antibodies to that, and then I'll make the reaction happen faster. And I can even look at it in, using an optical probe. That means I can actually look at, color sensitive detection. Look, if I have different nanoparticles and I'll attach different types of, let's say, antibodies to each of those nanoparticles, so that when I look at my red color, I see something slightly, blue shifted color. If I look at the optical signal, then I know what is happening at for a different antibody. So using just a small liquid, you inject and you can actually get a lot of information about various antibodies. So this is something that people are looking at. Another application is basically in cancer therapy. So we all, understand cancer, and it's very dangerous. And one of the treatments is to, let's say chemotherapy, or even irradiation with, high energy radiation, so that you kill the cancer cells. The problem is, if you irradiate, you're going to expose all of the body. It can kill the cancer cells, but it also kills the regular cells, which is not good. So it turns out that if you, let's say, inject a particle, this is done in, I think, rats, wherein, let's say, it has a tumor, and then you inject this solution containing nanoparticles, and these nanoparticles are very, very sensitive to, they are sensitive to IR radiation, and then I inject locally. So I'll try to attach some elements to this, molecules to this nanoparticle, such that they go and attack the cancer cells. They attach themselves to the cancer cells. Now I'll simply shine light, okay, and wherever I have a nanoparticle, I'm going to heat it up, because there's a hot spot, right? The electromagnetic energy is going to be confined there. So I'm going to kill the cells which are connected to this injected solution, and everywhere else there is no nanoparticle. I'm shining a normal amount of light. There is no hotspot. The cells are not affected. So it's a very nice way of actually targetedly attacking cancer. I mean, there are some clinical trials going on in the US, especially I think from the group of Professor Naomi Halas, who has been looking at it for a long time now. All right. So there is some of these ideas, of these plasmonics that are already into. People are looking at applications. All right. So this is what I have so far. So this I'll conclude here. I'll stop, and then so what we have done is we have looked at LSPR in sufficient depth. In the next lecture, I'll take it forward from there, and then we'll look at what is known as surface plasmon polariton. We'll look at that. All right. Thank you so much.